Welcome back everyone to part 3 of our basic PyTorch neural network. In part 3, let's go ahead and evaluate our model's performance on data it's never seen before, such as the test data set. Then we'll go ahead and show you how you can save the model, load it back up, and then we'll also show you how you could predict on a completely new unseen data point. A question students often ask me is, hey, I have a single data point, how do I actually predict what class it belongs to? So we'll show you how to do that. Let's get started. All right, so here we are where we left off last time in the notebook. And now what we want to do is we want to validate the model on our test set. Remember the test set, those are data points that the model has never seen before. So it's going to be useful to evaluate it on that test set. And what we do is we say with torch.no underscore grad colon. And basically what this command does, torch.nograd, is that is going to impact that auto gradient engine and essentially deactivate it. So it's telling PyTorch, hey, you don't need to worry about back propagation right now because I'm just evaluating. I don't need you to go back and change those weights and biases based off my test data. So that essentially turns it off. And what's nice about that, it reduces memory usage and also speeds up computation because PyTorch is essentially just going to take this testing data, run it through your network that already has its trained weights and biases, and then spit back out what it thinks the result should be. So our Y evaluation is going to just then be equal to model dot, and we'll say forward on our X test. So X test, those are the features from our test data set. And now we have essentially our predictions on that test set, those Y evaluations. And then let's go ahead and get the loss off that, or the error. We'll say criterion, and then pass in Y eval against Y test. So we run that, and then we can actually just check out the loss. And so it looks like the loss on our test set is 0.058. And if you're getting slightly different results, that's totally okay because depending on how many times you run this, or if you ran a cell more than once, or if you use a different random state, your weights and biases, because they have a random initialization, could be slightly different. So don't worry if you're slightly different than this, but you should be somewhere in the range of 0.04 to 0.07. And luckily for us, this loss on our test data set looks to be pretty similar. In fact, it's actually performing better than the loss on our training set. So we can see here we're getting kind of a similar loss value, somewhere hovering around 0.06. So that indicates good performance and that you're not overfitting to the training data. If you overfit to the training data, then when you evaluated test data, you'd have some sort of huge loss. But this basically tells us and implies that when we're running our testing data, we're actually reaching some sort of similar loss that we did on our training data. Okay, so let's imagine that you actually kind of want to print out the results here on this test data set. Something you can do here is I'll go ahead and say correct is equal to 0. So we're actually going to see how many flowers did we actually evaluate correctly. So again, we'll say with torch dot no underscore grad, so don't run that gradient engine. We'll say for I comma data, and we're going to enumerate X test. I'll grab those predictions. So model.forward data. So now let's go ahead and print out what our model is doing as it runs through this test data set. So I'm going to do a little bit of print formatting here, and you don't need to do it exactly like this, but I'll say my data point at I+1. So essentially I want to show, in fact, we don't even need to say data. We can just say I+1 and then maybe something like that. So essentially this is going to print out 1 colon and then 2, excuse me, not colon, parentheses. So 1 dot parentheses, 2 dot parentheses, 3 dot parentheses, and so on. In fact, I can just run this right now and you'll see what this is printing. So 1, 2, 3, 4, etc. And then what I'm going to print in the same line is yval. And because yval is a tensor, you're not going to be able to print it directly until you pass it in to str. So now let's go ahead and run that. And you can see here the tensor that's actually being returned, where the highest value indicates the likelihood that the network thinks that class it belongs to. So if this class is class 0, this is class 1, and this is class 2, we base it off index position, the network is going to predict that it should belong here in class at index 1 because that has the highest value. And what we can also do then is print along test of the current I. So then if we print that, we can see the actual class. So 1, we can see 1 was the highest value and so on, etc. So if you really wanted to kind of keep going on this, you could then print out yval max and then compare its index position and so on. But we'll just go ahead and do this. Just a little bit of formatting here. Run that, and you can kind of see the results. And you can check out the notebook. We add in some more kind of complex string formatting just so these spaces are all even. But hopefully you get the idea here. Essentially, we get back this tensor at the very end due to the fact that if you scroll back up here, recall that we were using cross entropy loss. So cross entropy loss, what it ends up producing for us at the end of the day is this tensor. Recall that last output layer had 3 values, and the greatest value is going to be at the index position of what class the network thinks that particular flower belongs in. And here we have the actual correct value. So let's count up how many of these we actually got correct. So kind of a straight up accuracy score. So we start off with correct is equal to 0, and then we'll do the following. We'll say if yval.argmax item, essentially grabbing the actual index position of that max value, we'll say if that's equal to ytest at I, then go ahead and add 1 to correct. And then after this whole for loop is done, we'll just go ahead and print out those values. We'll say we got blank number correct. So you go ahead and run that, and then at the end of all this, you should see we got 30 correct. So it looks like based off my random initializations, it actually performed perfectly on the test data, which is pretty awesome. And again, you may get 1 wrong depending on what actual random states you started. And if you actually run our lecture notebook, you should get 1 wrong. I believe it misclassifies a number 17 here. Okay, and again, if you wanted to actually print out the predicted classification directly, instead of printing out string yval, you could print out string yval argmax item. So you could just grab this and stick that in there, run that, and that basically shows you the predicted value or predicted class versus the true class. So you can kind of go around here, and for this particular case, we get 30 out of 30 correct, which is pretty awesome. All right, finally, let's show you how to save the trained model to a file. And luckily, PyTorch makes this easy. You simply say torch save, and you go ahead and say model dot, and you say state underscore dict. So this is passing in the state dictionary of that particular model. And then what we're going to do here is pass in a string of what we want this to be called. So go ahead and name it something like my iris model.pt. So it's a PT file. So right now, remember that model object has been trained and validated. It looks like it's performing really well. So what we're going to do now is we save it to the disk. And if you want to save it in some other directory on your computer, you simply just pass in the entire directory here. So you could say something like my C drive, users, etc., my models, and you can pass in the entire file path. If you just pass in .pt and some string, it will save it to wherever this notebook is located. Okay, so we go ahead and save this state dictionary, which essentially are the learned parameters of the model. So we'll go ahead and run that. So that is now saved. So I'm going to create a new model. And recall, if I were to instantiate a new model, this model has kind of no idea what the weights or the biases should be. So then I can take that new model and then say load a state dictionary. So I'll say new model.load state underscore dict. And then I say torch load, and then I pass in whatever I happen to save. So in this case, it's this string right here. We will pass it in. We run that, and if we want to confirm that everything worked, we can say model eval, and it'll return back what the model actually looks like. Now keep in mind, loading and saving a state dictionary assumes that you still have the original model class. So keep that in mind. If you actually just want to save the entire model, including its class and parameters, then you have to save it as a pickle file. And in that case, instead of passing in the state dictionary, you just pass in model directly. Okay, so keep that in mind. If you wanted to save just that state dictionary, essentially the weights and biases after it's been trained, you say state dictionary. If you want to save the entire model, assuming if you scroll back up here that you weren't going to have future access to this particular class, then you save, instead of saying state dictionary, you just say save the model. So you would remove this highlighted line of code and just say something like this, and you would save it as a pickle file. Okay, you can check out our lecture notebook. We have kind of a whole little rundown, as well as a link to the official documentation on that. So again, here's our lecture notebook. Underneath, save the trained model to a file. We have this whole little discussion for you, the 2 different methods, and then a nice little link to the tutorial of saving and loading models. Overall, it's pretty straightforward. And finally, let's go ahead and see how we can use this model on brand new, totally unseen data. A really common question my students ask me is, how do I actually classify some new single flower? If we were to pick a flower out of the field, we measure its dimensions, and I want to feed it into the network and ask the network, hey, what is this? The way we do that is, first, let's go ahead and define our mystery flower. We'll say mystery iris, and I'm going to set that equal to, let's say, torch tensor, and we'll give it 4 features for that sepal length, sepal width, petal length, and petal width. So I'm actually choosing kind of specific values here. And then what I will do is I'll go ahead and plot that out. Recall that at the very top of our notebook, we plotted out the flower classes. What I want to do is plot out a little point so that I can see my new class, or my new flower, that single mystery iris. So I will copy and paste the code again from the notebook. And our lecture notebook has this one extra line, which essentially adds in a single scatter plot for that mystery iris point. We go ahead and run this, and you should see that mystery iris point as a yellow marker because I said color is equal to y. You can go ahead and change that if you want. But you can see here, it looks like it should be iris setosa. If you look at that mystery iris, it's really close to the iris setosa on these plots. So I would expect it to be classified as iris setosa. And iris setosa is at index 0. So let's try it out. How do we actually do this with our network? We again say essentially the exact same process we did on our test set, which makes sense because the test set is also unseen data as far as the trained network is concerned. So we'll say with torch.noGrad, we can either use our model that exists already, or we can use that new model that we loaded up. It's essentially the same thing. We can say new model, go ahead and pass in that mystery iris, and then let's go ahead and just print that out. So if you run that, it shoots back a tensor at you, and recall that the highest value at the index, so this index position has the highest value, aka class 0, which is setosa, is its prediction. And if you want the code to just print out that class straight away, you can go ahead and say new model, mystery iris, and then call argmax off of this. Run that, and it reports back kind of as a tensor, or if you want, you could then grab the item and so on, but it essentially reports back, hey, this is the max at class 0. All right, that's it for our basic PyTorch neural network. Coming up next, we're going to expand on a lot of the ideas we discussed here, but onto a much larger and realistic data set that also has categorical features. So we'll show you how to deal with all of that coming up in the next series of lectures. We'll see you there.